The most famous photograph in the history of astronomy is also its most misleading. Point the Hubble Space Telescope at a patch of sky you could cover with a grain of sand held at arm's length. Keep the shutter open for 11 days. The image that comes back shows over 10,000 galaxies crammed into a frame smaller than your fingernail. Spirals tilted at elegant angles, ellipticals glowing like lanterns, smears of light scattered between larger structures like debris from a distant explosion. Your brain looks at this image and does something perfectly reasonable and completely wrong. It sees neighbors. It sees a crowded room, a densely packed cosmos of nearby structures separated by manageable distances, a universe that feels full. That impression is one of the most persistent lies in all of science. The truth is that the dominant feature of the observable universe is not the galaxies. It is the emptiness between them. Emptiness so vast, so total, and so actively growing that the word separation barely applies. And when you understand what that emptiness actually is, not as a poetic abstraction, but as a measured physical reality, the universe becomes a fundamentally lonelier place than any photograph will ever suggest. To understand intergalactic distance, you first need to hold in your mind the scale of a single galaxy, not as a label, not as a glowing shape in a deep field image, but as a physical object with a real size that already exceeds anything the human mind was built to comfortably hold. Our galaxy, the Milky Way, is a barred spiral containing somewhere between 200 billion and 400 billion stars. Each of those stars is a thermonuclear furnace. Many of them are orbited by planets, moons, asteroids, and comets in numbers that likely run into the trillions. The entire structure spans roughly 100,000 to 200,000 light-years from edge to edge, depending on how you define the boundary. Some measurements that include the faint outer stellar halo and the dark matter envelope push that number considerably higher. A light-year is the distance light travels in 1 year, approximately 6 trillion miles. At the speed of light, which is 186,000 miles per second, the fastest speed permitted by the known laws of physics, crossing the Milky Way from one edge to the other would take 100,000 years. That single fact deserves to sit in the mind for a moment. Light is not slow. It crosses the distance from the Earth to the Moon in about 1¼ seconds. It reaches the Sun in roughly 8 minutes. It passes the orbit of Neptune in about 4 hours. Yet this same light, traveling at the absolute cosmic speed limit, would need 100,000 years to traverse the structure you live inside. When the light now arriving from the far edge of the Milky Way began its journey, modern humans had not yet left Africa. The species Homo sapiens did not exist in its current form. Entire civilizations have risen and fallen in the time it takes a single photon to cross our galactic home. 100,000 years, 1,300 human lifetimes end to end. That is the diameter of a single galaxy, one island of stars, one structure in a cosmos containing an estimated 2 trillion of them. Now hold that scale firmly in mind, because the distances between galaxies are not measured in miles or even in individual light years. They are measured in multiples of galaxy lengths. And when you hear the first number, the gap between us and our nearest large galactic neighbor, the number is already devastating. On a clear autumn night in the northern hemisphere, look for the constellation Andromeda and find the faint, hazy smudge of light just off its boundary. That smudge is the Andromeda Galaxy. It is the most distant object visible to the unaided human eye. It appears small and faint and manageable. It is none of those things. Andromeda is a gravitational empire containing approximately 1 trillion stars. Its disk stretches across 200,000 to 260,000 light-years, comparable in size to our own Milky Way, and possibly somewhat larger. In January of 2025, NASA released a mosaic of Andromeda assembled from over 600 overlapping Hubble Space Telescope observations collected across a decade of work. That mosaic resolved approximately 200 million individual stars and still captured only a fraction of the galaxy's total stellar population. At its center sits a supermassive black hole with a mass exceeding 100 million times that of our Sun. Andromeda is not a small neighbor. It is a full-scale galactic civilization sitting across the void from our own. It is approximately 2.5 million light-years away. Say that slowly. 2.5 million light-years. A light-year is roughly 6 trillion miles. Multiply that by 2.5 million, and you arrive at a distance of approximately 15 quintillion miles. 15 followed by 18 zeros. The number has so many digits that it stops functioning as a number and becomes an abstraction. So let me translate it into something you can feel. In December of 2024, the Parker Solar Probe became the fastest human-made object in history, reaching a speed of approximately 430,000 miles per hour as it swung past the Sun. At that speed, you could travel from New York to Tokyo in under a minute. You could circle the entire Earth in about 3.5 minutes. This is the pinnacle of human engineering, the absolute fastest any machine built by our species has ever moved. At the speed of the Parker Solar Probe, the journey to the Andromeda Galaxy would take approximately 4 billion years. Not 4,000, not 4 million, 4 billion. That is roughly equal to the current age of the Earth. You would need to travel at the fastest speed humanity has ever achieved, without pausing, without decelerating, for a duration equal to the entire geological history of our planet, just across the gap between two galaxies that astronomers describe as neighbors. Even light, traveling at 186,000 miles per second without rest, needs 2.5 million years to make that crossing. If you could fire a laser beam toward Andromeda right now, those photons would not arrive until 2.5 million years from now. Whatever civilization sent that signal would almost certainly be unrecognizable or extinct before a single photon completed the trip. The gap is not merely far, it is temporally ruinous. It dismantles any meaningful concept of timely contact, let alone physical travel. And here is the part that truly breaks intuition. Andromeda is close. By galactic standards, it is practically next door. It is our nearest large spiral galaxy, our most immediate peer, the galactic structure most likely to interact with us in the foreseeable cosmic future. In roughly 5 to 7 billion years, Andromeda and the Milky Way are expected to collide and merge into a single massive elliptical galaxy. A 2026 analysis using the latest proper motion data raised the merger probability to approximately 90%, with a median merger time of roughly 6.5 billion years. These two galactic empires, each spanning hundreds of thousands of light years, each containing hundreds of billions of stars, are already falling toward each other under mutual gravitational attraction at roughly 250,000 miles per hour. Their merger is confirmed, it is measured, it is real. And the gap between them is still so enormous that their approach speed, impressive as it sounds, barely registers against the distance remaining. Two galaxies in confirmed gravitational partnership, actively approaching one another at 250,000 miles per hour, will not meet for billions of years. Their reunion requires more time than our sun has left to burn. The fun sparked and concluded. All of it happened while those photons were still in transit, still crossing the emptiness between here and there. And Andromeda is merely the nearest large member of our local galactic family. The Milky Way belongs to a gravitational association called the Local Group, a collection of galaxies bound together by their mutual gravitational attraction. As of the most recent surveys, the Local Group contains approximately 142 confirmed members. That sounds like a dense neighborhood. It is not. The vast majority of those members are tiny dwarf galaxies containing only a few billion or even a few million stars each. Many of them orbit the Milky Way or Andromeda as satellites, trapped in gravitational bondage like moons circling a planet. The third largest member, the Triangulum Galaxy, contains roughly 40 billion stars and sits about 2.7 million light-years from us. Beyond these three dominant spirals, the Local Group is mostly populated by dim, small, easily overlooked structures scattered across a volume of space roughly 10 million light-years in diameter. 10 million light-years. That is the size of our so-called neighborhood. The distance across the Local Group from one edge to the other is approximately 100 times the diameter of the Milky Way itself. Imagine being told that the nearest house to yours is 100 house lengths away, not 100 feet, 100 times the entire size of your home. That is the kind of spacing we are talking about. And this is the densest galactic environment anywhere near us. Even within this tightly bound family, the gaps are staggering. The Large Magellanic Cloud, one of the closest satellite galaxies to the Milky Way, sits roughly 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years distant. These are satellites of our own galaxy, gravitationally bound to us, orbiting within our extended halo. And they are still so far away that light needs hundreds of thousands of years to make the trip. The Sagittarius Dwarf Elliptical Galaxy is closer, only about 70,000 light-years from our galactic center, but it is in the process of being torn apart by the Milky Way's tidal forces. It is not a neighbor so much as a victim, a smaller galaxy being gradually consumed by our own. What people rarely confront is what the space between these galaxies actually is. When you look at a diagram of the local group, your brain treats the labeled dots the way it treats a roadmap. It sees implied routes between them. It assumes the space between the dots is filled with something. It is not. The interstellar space within a galaxy, the space between individual stars, already represents a vacuum so extreme that no laboratory on Earth has ever come close to replicating it. A typical region of interstellar space within the Milky Way contains roughly 1 million hydrogen atoms per cubic meter. The air you are breathing right now contains approximately 25 trillion molecules per cubic meter. The space between stars is already a void so profound, it would kill you in seconds if you were exposed to it. And compared to the space between galaxies, interstellar space is practically dense. Intergalactic space contains approximately 1 atom per cubic meter. 1 atom. In a volume of space the size of a large washing machine, you would find a single hydrogen atom. The rest is pure, featureless, uninterrupted void, stretching for millions of light years in every direction. According to measurements from the Harvard-Smithsonian Center for Astrophysics, the intergalactic medium has a density less than a billionth of the density of air at sea level. Intergalactic space is roughly 1 million times emptier than the space between stars. That is not a gradual increase. That is a leap to a completely different category of emptiness. If interstellar space is a desert, intergalactic space is a desert the size of a continent with nothing in it but a single grain of sand. And then the desert keeps going. Now imagine being placed at the midpoint between the Milky Way and Andromeda, roughly 1.25 million light years from either shore. Your suit is intact. Your instruments function. Your eyes adjust. And what you see is nothing, not the comfortable darkness of a clear night on Earth, where thousands of stars provide a canopy of light. An absolute, featureless, unyielding blackness that extends in every direction without interruption. The Milky Way behind you appears as a pale, hazy oval, smaller than your thumbnail held at arm's length. Andromeda ahead looks similar, a faint grey glow. In every other direction there is nothing. No nebulae, no star clusters, no milky band of combined starlight, just void. Your instruments confirm what your eyes already suspect. There is functionally nothing here. You could extend your arms in every direction and sweep through a volume of space larger than a building without your gloves. Touching a single atom, you could wait 1 billion years in this location and the view would not change. No star would drift close enough to become visible. No structure would form. The void is patient. It does not evolve or fluctuate or offer any hint that it will ever be anything other than what it is. The intergalactic medium is not completely empty in the absolute physics sense. Cosmological models predicted decades ago that the process of galaxy formation would heat enormous quantities of gas and scatter it through the cosmic volume in a diffuse hot plasma, known as the warm, hot intergalactic medium. For years, this material was effectively missing. Astronomers could account for the ordinary matter locked inside galaxies and stars and gas clouds. They could measure matter in galaxy clusters where hot gas glows in X-rays. But when they added it all together, roughly half the ordinary matter the universe should contain was unaccounted for. In 2018, observations of highly ionized oxygen atoms in the spectra of distant quasars provided strong evidence that this diffuse plasma exists along sightlines through the void. In 2020, measurements from fast radio bursts confirmed it. Roughly 40 to 50% of all the normal matter in the universe appears to be suspended in a hot, impossibly thin haze spread across the cosmic web between galaxies. And even with that discovery, even with half the universe's ordinary atoms distributed through the intergalactic medium, the density remains staggeringly low. The warm, hot intergalactic medium contains between 1 and 10 particles per cubic meter in its densest filamentary regions. In the deep voids between those filaments, the density drops even lower. You could fill a volume of intergalactic space equal to the entire Earth, and the total mass of ordinary matter inside that sphere would weigh less than a large commercial aircraft. The universe took half its ordinary matter and smeared it across volumes so vast that the matter became functionally invisible, heated to millions of degrees, and dispersed so thinly that it cannot form anything. No stars, no planets, no chemistry, no structure. Just an ethereal plasma haunting the darkness between galaxies. Like a ghost of matter that might have become something, if it had not been scattered across an emptiness too large to allow collapse. The temperature of this void adds a final layer of strangeness. The intergalactic medium, despite containing almost nothing, registers temperatures of millions of degrees. This sounds contradictory until you understand that temperature in physics describes the average kinetic energy of particles, not the transfer of warmth. With so few particles per cubic meter, there is no meaningful heat exchange. You could float in intergalactic space and freeze to death, surrounded by particles technically hotter than the surface of the sun. The void between galaxies is simultaneously scorching and frozen, energetic and lifeless, technically filled and practically empty. It is a place where the normal categories of physical experience break down entirely, where the concepts of hot and cold and full and empty lose their intuitive meanings and become technical labels applied to conditions no human was ever meant to encounter. The reason all of this matters, the reason the emptiness transforms intergalactic distance from an impressive number into something qualitatively different, is that it changes the nature of the separation. Stars within our galaxy are part of a shared gravitational structure. They orbit the same center. They exist within the same interstellar medium, the same magnetic environment. The space between them is sparse, but it is a medium in a meaningful sense. There is continuity between origin and destination. They belong to the same place. The gap between the Milky Way and Andromeda severs that continuity completely. It is not a long hallway connecting two rooms. It is an ocean with no water. There is no shared structure, no continuous medium, no gravitational bridge you can follow from one galaxy to the next. They float in isolation, separated by voids so total that the word between barely captures the reality. To understand how those voids came to exist, you have to go back to the very beginning. In the first few 100,000 years after the Big Bang, matter was distributed almost uniformly across all of space. Almost, but not perfectly. Tiny quantum fluctuations in the density of the infant universe, variations of roughly 1 part in 100,000, created regions that were ever so slightly denser or slightly less dense than average. Gravity took over from there. Regions with slightly more matter pulled in additional material from their surroundings, growing denser over time. Regions with slightly less matter lost material to their denser neighbors, becoming emptier over billions of years. This process of gravitational instability amplified those minuscule initial differences into the dramatic cosmic web we observe today. Dense regions collapsed into the filaments and nodes where galaxies formed. Underdense regions expanded into the voids. The quantum fluctuations that seeded the voids were unimaginably small. A variation of 1 part in 100,000 is so slight that if you represented the average density of the early universe as a perfectly flat lake, the fluctuations would correspond to ripples less than a millimeter high on a surface stretching from one end of the Earth to the other. Yet those infinitesimal ripples, amplified by gravity over 13.8 billion years of cosmic evolution, became the voids and filaments and clusters that define the structure of everything we can observe. The largest empty spaces in the universe trace their origin to the smallest possible variations in the density of the newborn cosmos. The cosmic web that gravity built from those fluctuations consists of 4 distinct components. Dense nodes at the intersections where multiple streams of matter converge. Regions where galaxy clusters form with masses equivalent to quadrillions of suns. Connecting the nodes are filaments, long thin threads of dark matter and gas stretching across tens or hundreds of millions of light years. Where filaments intersect at broad angles, they form walls, sheet-like concentrations of galaxies spanning hundreds of millions of light years. And then there are the voids. Cosmic voids are the dominant feature of the universe. They are not small gaps between clusters. They are enormous, roughly spherical regions of space where the density of matter drops far below the cosmic average. Typical voids measure between 30 and 300 million light-years across. The largest confirmed supervoids exceed 300 million light-years in diameter. Collectively, voids account for approximately 80% of the total volume of the observable universe. 80%! When you look at a deep-field photograph and see galaxies scattered across the frame, you are seeing the 20%, the bright fraction, the thin walls and narrow filaments where matter managed to concentrate. The other 80%, the overwhelming majority of the universe by volume, is void. Empty. Dark. Structureless. The universe is not a room full of galaxies. It is an ocean of emptiness, with galaxies clinging to its surfaces like foam on the waves. One of the starkest examples of this architecture is the Booter's Void, discovered in 1981 by astronomer Robert Kirshner and his team during a survey of galactic redshifts. The Booter's Void is a roughly spherical region of space approximately 330 million light-years in diameter, sitting about 700 million light-years from Earth. Inside this enormous volume, astronomers have found approximately 60 galaxies, 60 in a region where the cosmic average would predict roughly 2,000. The Booter's Void is so empty that if the Milky Way sat at its center, humans would not have discovered the existence of other galaxies until the 1960s, when telescope technology finally became powerful enough to detect objects at the distances required to see beyond the void's boundaries. For most of human history, looking outward from the center of the Booter's Void, the sky would have appeared to contain nothing but our own stars. The universe beyond would have been invisible. The very concept of other galaxies would have seemed absurd, because the evidence would have been hidden behind a wall of emptiness too deep for telescopes to penetrate. The Booter's Void is not unique. It is simply one of the largest known examples. The KBC Void, the structure in which our own Milky Way appears to reside, stretches approximately 2 billion light-years across, with a density roughly 20% lower than the cosmic average. The local void, an emptier region adjacent to our own galactic neighborhood, extends roughly 200 million light-years and has been shown to influence the motion of our galaxy, pushing us away from its center at hundreds of thousands of miles per hour. Wherever astronomers point their instruments and map the three-dimensional distribution of galaxies, they find the same pattern. Matter concentrates into thin filaments and walls, and between those structures lie enormous bubbles of almost nothing, cosmological. Surveys show that typical filaments measure only about 20 million light-years in width while stretching across hundreds of millions of light-years in length. They are cosmic threads, disproportionately long and impossibly narrow compared to the voids they border. And the voids are not passive features of the landscape. They are growing. Cosmic expansion stretches all of space, but the effect is most dramatic in regions where there is little gravity to resist it. In dense filaments and galaxy clusters, gravitational attraction slows or halts the expansion locally, but inside voids, where matter is sparse and gravity is weak, dark energy drives accelerating expansion essentially unopposed. Voids are expanding faster than the cosmic average. They are growing larger, becoming emptier, and pushing the galaxies on their borders farther apart. The cosmic web is not a static structure. It is a dynamic architecture in which the voids are winning. This means the isolation between galaxies is not a fixed condition. It is worsening. The voids that separate galaxies today will be larger tomorrow and larger still a billion years from now. The filaments that connect clusters will stretch thinner. Dark energy is reshaping the cosmic web in real time, slowly dissolving the connections between structures and enlarging the empty spaces that divide them. The universe is not merely empty, it is becoming emptier. The architecture of isolation is deepening with every passing era of cosmic time. Now consider the implications for actually crossing those gaps. There is a moment in every honest confrontation with intergalactic distance where the mind shifts from understanding to something closer to surrender. Set aside all current engineering limitations. Forget chemical rockets, ion drives, solar sails. Grant the most generous scenario imaginable and assume a civilization has built a spacecraft capable of traveling at 90% of the speed of light. That is not a realistic prospect for humanity in any foreseeable future, but grant it anyway. A ship moving at 90% of light speed would be the most extraordinary machine ever conceived. It would cross the distance from Earth to the Sun in about 9 minutes. It would leave the solar system in hours. It would reach the nearest star in under 5 years. Now point that ship toward Andromeda. At 90% of the speed of light, the journey to Andromeda would take approximately 2.8 million years as measured by an observer watching from Earth. The ship itself, thanks to relativistic time dilation, would experience a shorter journey. At 90% of light speed, the dilation factor compresses onboard time by roughly a factor of 2.3. The crew, if somehow kept alive, would experience the passage of approximately 1.2 million years. This is not a rounding error. It is a duration that exceeds the entire span of the genus Homo on Earth. Every human ancestor who ever lived, from the first toolmakers to the last person born before the ship launched, would fit inside a fraction of the onboard travel time. What if the ship traveled faster? At 99% of the speed of light, time dilation compresses the onboard experience more aggressively by a factor of about 7. The crew would experience roughly 350,000 years, still an eternity, still longer than modern humans have existed. At 99.9% of light speed, the dilation factor rises to about 22, reducing onboard time to approximately 113,000 years. Better, but still a span during which entire civilizations could rise, flourish, collapse, and be forgotten dozens of times over. Even at 99.99% of light speed, a velocity so extreme that the energy required to achieve it approaches the total mass energy of the spacecraft itself. The crew would still experience tens of thousands of years of travel. No version of this calculation produces a human-scale journey. The distance is simply too enormous for even the most extreme relativistic effects to compress it into anything manageable, and the energy required to reach these velocities is itself a barrier that sits at the boundary between ambitious and physically absurd. Accelerating even a modest spacecraft to 90% of light speed demands energy quantities that dwarf the total output of human civilization. The kinetic energy of a single kilogram of matter moving at that speed is approximately 117 quadrillion joules. The total energy consumption of all human civilization in a single year is approximately 580 exajoules. Accelerating a modest 10,000 kilogram spacecraft to 90% of light speed would require roughly 1.2 times 10 to the 21st joules, an amount equivalent to more than 2,000 years of total human energy production. For a ship massive enough to sustain a crew across millions of years of travel, the figure climbs by orders of magnitude. And this calculation assumes perfect efficiency. Real propulsion systems are nowhere near that efficient. The gap between what we can build and what intergalactic travel demands is not a gap that incremental improvement can close. But even if the energy problem were solved, even if a civilization somehow harnessed the output of its star and built the impossible ship, the journey itself would render the mission meaningless in almost every practical sense. No biological organism can survive a duration of hundreds of thousands of years. No mechanical system built from known materials can remain functional across geological timescales without maintenance and replacement. The ship would need to be not a vessel, but a self-sustaining world capable of enduring longer than most species persist on Earth. The crew that arrived at Andromeda would bear no meaningful resemblance to the crew that departed. They would be a different species shaped by 1,000,000 years of isolated evolution in a metal shell crossing the void. And the civilization they left behind would be gone. 2.8 million years would pass on Earth between departure and arrival. Whatever culture launched the ship would have transformed beyond recognition or vanished entirely long before the first signal came back. There would be no one to receive the report. The ship would arrive at a galaxy full of 1,000,000,000,000 unfamiliar stars, carrying the descendants of a civilization that no longer existed, reporting to a home that had forgotten they were coming. And Andromeda is the easiest target. It is the nearest major spiral. For galaxies beyond the local group, the numbers escalate into outright absurdity. The Virgo cluster sits 54 million light-years away. At 90% of light speed, the journey would take 60 million years, as measured from Earth, and roughly 26 million years on board. The Coma cluster, a rich concentration of galaxies, lies 320 million light-years distant. The trip would consume over 350 million years, a duration stretching back to the early Carboniferous period on Earth, an era when shallow seas covered much of the continents and the earliest four-limbed creatures were still adapting to life on land. But the truly devastating blow to any concept of intergalactic connection does not come from distance or energy or time dilation. It comes from the universe itself. Space is expanding, not metaphorically, not in the sense that galaxies are flying apart through a static void. The fabric of space-time is stretching, increasing the distance between all points that are not gravitationally bound together. Every second, the space between galaxies grows. Every moment, the void gets wider. And the farther away a galaxy is, the faster the space between it and us expands. This relationship is described by Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance. The proportionality constant, the Hubble constant, currently measures approximately 67 to 73 kilometers per second per megaparsec, depending on which measurement technique is used. The exact value remains a subject of active scientific debate, a discrepancy known as the Hubble tension. But the implications of the law are not in dispute. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity of a galaxy increases by approximately 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. The speed of light is approximately 300,000 kilometers per second. At a distance of roughly 14 billion light-years, the recession velocity of a galaxy equals the speed of light. Beyond that distance, galaxies recede faster than light can cross the expanding gap between us. This does not violate Einstein's theory of relativity. Relativity prohibits objects from moving through space faster than light. It says nothing about space itself, stretching at any rate it pleases. Galaxies beyond the Hubble radius are not moving through space at superluminal velocities. They are sitting relatively still in their local patch of space-time, while the space between us and them expands faster than light can cross it. The consequence is absolute. The cosmic event horizon, the true line of no return, is the distance beyond which light emitted right now will never reach us, no matter how long the universe endures. It currently sits at approximately 16 to 18 billion light-years. The observable universe extends 46.5 billion light-years in every direction. The reachable universe, the portion we could theoretically still touch if we departed at light speed today, is a small bubble inside that larger sphere. Current estimates suggest that only about 6% of the galaxies within the observable universe remain theoretically reachable. The other 94% are already gone, receding too fast, separated by space expanding too rapidly for even light to bridge the gap. They are visible but untouchable, observable but permanently isolated, 94%. Out of the estimated 2 trillion galaxies in the observable universe, approximately 1.9 trillion of them are already beyond the reach of any signal, any spacecraft, any message we could ever send, even at the speed of light. Even starting today, the light we see from them is a fossil, a record of where they used to be when the universe was younger and smaller. The galaxies themselves, as they exist right now, have long since crossed the boundary into permanent isolation. To make that number visceral, the Milky Way alone contains somewhere between 200 billion and 400 billion stars. It is one galaxy. The 1.9 trillion galaxies we can never reach contain collectively somewhere in the neighborhood of 100 sextillion stars. Each of those stars may host planets. Each of those planets may harbor conditions suitable for chemistry, for biology, for the emergence of life and intelligence. And every single one of them is forever sealed behind a horizon of expanding space that no signal can penetrate. Whatever exists out there, whatever civilizations may have arisen, whatever wonders may have been built, they are as inaccessible as if they existed in a separate universe entirely. In every practical sense they do, and the situation is getting worse. Dark energy, the mysterious force driving the acceleration of cosmic expansion, ensures that the reachable universe shrinks with every passing moment. Galaxies currently within the cosmic event horizon will eventually cross beyond it as the expansion carries them farther away. With every year that passes, hundreds of millions of additional stars slip beyond the reachability threshold. Entire galaxies are crossing the boundary and vanishing from the set of objects we could ever theoretically contact. Within 100 to 150 billion years, every galaxy outside the local group will have receded beyond the cosmic event horizon, permanently. Even communication within the reachable fraction faces constraints that make meaningful exchange essentially impossible. Sending a message to Andromeda would take 2.5 million years at the speed of light. A response, if anyone were listening, would take another 2.5 million years to return. A single round-trip exchange would consume 5 million years. No conversation is possible, no negotiation, no cultural exchange, no alliance, no warning. The communication delay turns every interaction into a monologue, delivered to an audience that may not exist by the time the words arrive. A message sent to the Virgo cluster would take 54 million years to arrive. A round trip would consume over 100 million years, long enough for entire branches of the evolutionary tree to appear and go extinct in the intervening time. And even these grim figures understate the problem, because messages themselves face an additional enemy. Cosmic expansion stretches the wavelength of any signal in transit. A radio transmission sent at a specific frequency will arrive at its destination with a longer wavelength and lower energy than it started with after millions or billions of light years of travel through expanding space. Over sufficient distances, the expansion does not merely delay the message, it degrades it, it erases it, stretching the signal to wavelengths so long that it becomes indistinguishable from the background noise of the cosmos. What this adds up to is a universe that is not merely large, but structurally partitioned, divided into islands of matter surrounded by expanding voids that no technology consistent with known physics can bridge. The local group is our island. The Milky Way, Andromeda, Triangulum, and approximately 130 smaller galaxies comprise our gravitationally bound family. These galaxies are close enough and massive enough that their mutual gravitational attraction overcomes the cosmic expansion. They will not fly apart. They will not recede beyond the cosmic event horizon. Over the next several billion years, they will merge, interact, exchange stars and gas, and eventually collapse into a single enormous structure. Everything else is leaving. The Virgo cluster, the nearest major galaxy cluster, is gravitationally unbound from the local group. Cosmic expansion is carrying it away. The Laniakea supercluster, the immense structure to which the local group belongs, is not a gravitationally bound system despite its name. It is a flow pattern, and the expansion of space will eventually overwhelm even those flows. The cosmic web is not a permanent architecture. It is a transient arrangement of matter that exists only because the universe is still young enough for gravity to compete with expansion. In the deep future, expansion wins. The web dissolves. The filaments stretch beyond coherence. The walls disperse into the void. Each gravitationally bound island finds itself alone in a darkness that grows wider every second. The universe was not built for intergalactic connection. It was built with rules that guarantee intergalactic isolation. The speed of light creates a maximum velocity. The expansion of space creates a minimum rate at which distances grow. Dark energy creates a floor beneath which that expansion cannot fall. These three constraints, woven into the deepest physics of the cosmos, produce a universe in which galaxies are born into isolation and remain there permanently. The distance between them is not a problem to be solved. It is a structural feature of reality. Now sit with what that future will actually look like. Over the next several billion years, the galaxies of the local group will combine. The Milky Way and Andromeda will merge. Their stars will mingle. Their dark matter halos will fuse. Over tens of billions of years, the entire local group will settle into a single massive elliptical structure. Astronomers have already given it a name, Milkomeda, sometimes called Milkdromeda. It will be an enormous object, containing the combined stellar populations of both spirals and every dwarf galaxy in the local group, its elegant spiral arms erased by the chaotic violence of repeated mergers. Its stars orbiting in random directions around a massive central core, and it will be utterly, permanently, cosmically alone. By the time Milkomeda has fully formed, roughly 10 billion years from now, every galaxy outside the local group will be receding at ever-increasing velocities. The nearest galaxy clusters will have drifted hundreds of millions of light years farther away than they are today. The filaments of the cosmic web will have stretched beyond recognition, their matter dispersed into the expanding void. Within 100 to 150 billion years, every galaxy beyond the local group will have crossed the cosmic event horizon. Their light will have redshifted to wavelengths so long that no conceivable instrument could detect them. The cosmic microwave background itself will have faded beyond detectability, its photons stretched to wavelengths so long and its intensity diluted so thin that no instrument could distinguish it from silence. A civilization, arising in Milkomeda, at that distant epoch would inhabit a galaxy containing perhaps 1 trillion stars surrounded by nothing. Their most powerful telescopes pointed in any direction would reveal only darkness. No other galaxies, no cosmic web, no filaments or clusters or walls, no background radiation from the Big Bang. Nothing that would suggest the universe ever contained anything beyond their own galactic borders. They would have no way of discovering that the universe is expanding because there would be no distant objects against which to measure the expansion. They would have no way of inferring the Big Bang because the evidence, for it would have been carried beyond their horizon by the very expansion it set in. Motion. They would develop their own cosmology based on the only data available to them. A single galaxy surrounded by infinite empty space. No expansion, no beginning, no other structures. Their physics might be brilliant. Their mathematics might be flawless. But their cosmology would be wrong. Not because of any failure of intellect, but because the universe would have removed the evidence they needed to reach the right answer. We know this because we can still see what they will not be able to see. We live at the moment when the evidence is still accessible. The cosmic microwave background still fills the sky. The large-scale structure of the cosmic web can still be mapped. Galaxies at distances of billions of light years can still be observed and studied. We are the last observers who will ever have access to the full picture, or at least as much of it as the current cosmic horizon allows. Every generation that comes after us, every civilization that arises in the deep future, will know less about the universe than we do now. The cosmos is not progressively revealing itself to the creatures that inhabit it. It revealed itself briefly, during a narrow window of cosmic time, and it is now in the process of taking that revelation back. The greatest story ever told, the story of how a hot, dense beginning gave rise to stars, galaxies, planets, and life, will be erased from the observational record. Not destroyed, not lost to decay, simply carried beyond the reach of any observer by the very expansion it set in motion. This is the cruelty buried inside the beauty of every deep field image. When you look at a photograph showing thousands of galaxies, you are looking at thousands of islands that will never know one another. Each galaxy in that image is a complete world unto itself, containing hundreds of billions of stars, trillions of planets, and possibly countless forms of life and intelligence. And each one is sealed inside a bubble of distance and expansion that renders it permanently inaccessible to every other galaxy in the frame. The image shows proximity. The physics guarantees isolation. The beauty and the horror occupy the same frame. Consider what this means for the question that haunts every serious discussion of cosmic scale. Are we alone? The question is usually framed in terms of biology. Is there life elsewhere? Are there other minds looking up at other skies and wondering the same things we wonder? But the distance between galaxies reframes the question in a way that cuts deeper than biology ever could. Even if life is common, even if every galaxy teems with civilizations, even if intelligence is a routine product of cosmic evolution, the distances ensure that none of it matters in any practical sense. Civilizations separated by millions of light years cannot talk to each other. They cannot visit each other. They cannot confirm each other's existence within any time frame that is meaningful to either party. They are alone in every way that the word alone has ever meant to any conscious being. A civilization in a galaxy 200 million light years away could be the most advanced, most compassionate, most curious society the universe has ever produced. It could have solved every problem that plagues our species. It could have built structures that would make our greatest achievements look primitive, and we would never know. Not because our telescopes are too weak, not because our transmitters are too quiet, because 200 million light years of expanding void sits between us, and nothing in the known laws of physics can carry a meaningful signal across that distance within the lifetime of either civilization. The void does not care how advanced either party is. It does not yield to ingenuity or determination. It is indifferent, absolute, and permanent, and we know more about this permanence than any previous generation. We can count the galaxies, we can measure their masses and their star formation rates and their chemical compositions. We can map the cosmic web across billions of light years. We can reconstruct the history of the universe from the Big Bang to the present moment. And all of that knowledge changes nothing about the fundamental isolation. Knowing a galaxy exists 200 million light years away does not bring it 1 meter closer. Understanding the physics of cosmic expansion does not slow the expansion by a single kilometer per second. We are the most informed observers any universe has ever produced, and we remain as unreachable from our cosmic neighbors as we were before we understood why. The universe contains an estimated 2 trillion galaxies, and it is lonely. Not lonely in the sentimental sense, lonely in the structural sense. The way a scattered archipelago of islands is lonely when the ocean between them is 10,000 times wider than any island. The islands exist. They are real. Some of them are enormous, containing billions of inhabitants and complex ecosystems. But the ocean is so vast, so deep, and so featureless that the islands might as well exist in separate realities. No bridge can span the water. No ship can survive the crossing. The architecture of isolation is not a flaw in the cosmic design. It is the design. The voids are not holes in the structure. They are the structure. And the galaxies, for all their billions of stars and their trillions of worlds and all the complexity they may contain, are just thin luminous residue clinging to the edges of an architecture built primarily from nothing. The campfire analogy comes close to capturing it. Every galaxy in the universe is a campfire. Some are small flickering things. Others are roaring bonfires throwing light across hundreds of thousands of light years. But between every campfire and every other campfire stretches a darkness so deep and so wide that no one sitting at any fire can see the glow of any other. The fires burn in absolute solitude. Each one heats its own small circle of space. Each one illuminates its own tiny sphere of matter. And beyond that sphere, in every direction, the darkness goes on. We sit at one of those campfires. The Milky Way, 400 billion stars burning in a spiral of light and gravity. Planets orbiting in habitable zones. Complex chemistry assembling itself into life on at least one world, and possibly on many more. Intelligence emerging, looking upward. Building telescopes, mapping the cosmos, asking the oldest question, is anyone else out there? The answer, as far as intergalactic distance is concerned, is that the question itself may be tragically premature. Even if the answer is yes, even if every galaxy contains civilizations, even if the universe is saturated with life from one end of the observable volume to the other, the distances ensure that each civilization sits at its own campfire, warming its hands against a cold that extends in every direction without limit. The campfires cannot see each other. They cannot reach each other. They burn alone, separated by the deepest and most permanent isolation the laws of physics can produce. What scientists are still working to understand, and what remains genuinely open, is the precise nature of dark energy, the force responsible for the accelerating expansion that deepens this isolation with every passing era. We know it exists. We can measure its effects with extraordinary precision. We can calculate the rate at which it is enlarging the voids and pushing galaxies apart. What we cannot yet explain is what dark energy actually is. Its physical origin remains one of the deepest unsolved problems in all of physics. If its nature were fully understood, it might in principle reveal whether the expansion will continue at its current rate, whether it will accelerate further, or whether some unknown physics might eventually alter the trajectory. The Stage 4 dark energy spectroscopic surveys currently underway and the upcoming Euclid Space Telescope mission are designed to constrain the properties of dark energy with greater precision than ever before, probing whether its strength varies with time or with position in the universe. These measurements will not make the voids smaller, but they will sharpen our understanding of why the voids exist and how they will evolve. Researchers are also making progress on mapping the intergalactic medium itself with increasing detail. Fast radio bursts, brief, intensely energetic pulses of radio waves from distant galaxies, are proving to be remarkable tools for probing the material spread between galactic structures. Each burst carries within it a signature of the electrons it passed through on its journey. By analyzing how different radio frequencies arrive at slightly different times, a phenomenon called dispersion measure, astronomers can reconstruct the electron density along each burst's path through the intergalactic medium. As the catalogue of fast radio burst detections grows into the thousands, these measurements are building a three-dimensional map of the material spread between galaxies with a resolution that was not possible even a decade ago. This work is revealing the fine structure of cosmic filaments and the true depth of the voids between them in ways that will refine our understanding of how the universe's matter is distributed. There is also active research into the question of what the cosmic web will look like as it continues to evolve. N-body simulations running on the world's most powerful computing clusters are tracking the evolution of the large-scale structure across billions of simulated years of future cosmic time. These models are revealing in detail how the filaments thin and how the voids grow, and at what point the connections between gravitationally bound structures finally dissolve. The results consistently confirm the broad picture. The isolation between galaxies is not a temporary condition that will resolve as the cosmos matures. It is the direction in which the universe is moving, the endpoint toward which its physics has always been aimed. Perhaps the most quietly profound aspect of all of this is something that rarely gets mentioned alongside the numbers. We exist at a privileged moment, not privileged in the sense of being special or selected, privileged in the purely temporal sense of having arrived at a point in cosmic history when the evidence for the universe's origins is still accessible, when the large-scale structure is still intact enough to be mapped, when the cosmic microwave background still fills the sky with information about the conditions that prevailed 13.8 billion years ago. The universe is not going to stay this legible. Every billion years that passes takes some of that legibility away. The questions that define modern cosmology: what is dark energy? How did the first galaxies form? What is the geometry of the universe on the largest scales? What happened in the first fractions of a second after the Big Bang? These questions can only be answered using the evidence the current epoch still provides. Later observers, arising in a cosmos where the voids have won and the horizon has closed, will not have this evidence. The questions may never occur to them. We are here. We can see 2 trillion galaxies. We can measure the expansion of space. We can trace the structure of the cosmic web back to the quantum fluctuations of the Big Bang. We can calculate that 94% of what we can see is already beyond our physical reach, and understand precisely why. That understanding itself, the ability to know the shape of the prism and describe it accurately, is perhaps the most remarkable thing our campfire has ever produced. The darkness around it is real. It stretches farther than any signal we send will ever travel. But the fire burns, and for now, it is still bright enough to see by. If you found this exploration useful, the most meaningful thing you can do is share it with someone who would find it just as striking. The next video will go somewhere equally unexpected. To fully appreciate why intergalactic distances have the meaning they do, it helps to understand how humanity came to know about them in the first place. For most of recorded history, the question of what lay beyond the Milky Way was not even recognized as a question. The ancient Greeks understood that the Earth was a sphere. They calculated its circumference with remarkable accuracy. They mapped the motions of the planets and built sophisticated geometric models of the solar system. But the concept of other galaxies, other island universes floating in the darkness beyond our own, was not part of any cosmology anywhere in the ancient or medieval world. The Milky Way was simply the sky. The stars were lights attached to a celestial sphere. The universe, as far as anyone knew, was approximately the size of the solar system, surrounded by a shell of fixed stars at some indeterminate but finite distance. The first serious cracks in this picture appeared in the early 18th century when astronomers began cataloguing fuzzy patches of light in the sky that refused to resolve into individual stars, no matter how powerful the telescope. These objects, called nebulae from the Latin word for cloud, accumulated in catalogues throughout the 1700s and 1800s. Charles Messier, a French astronomer primarily interested in comet hunting, catalogued over 100 of them in 1771, simply to avoid confusing them with the comets he was looking for. The Andromeda Nebula was among the most prominent entries. It was visible to the unaided eye and had been documented in Persian astronomical records as far back as 964 by Abd al-Rahman al-Sufi, who described it as a small cloud. For centuries, nobody knew what it was. The debate over the nature of these nebulae reached its most dramatic expression in the Great Debate of 1920, a formal scientific confrontation held at the Smithsonian Institution in Washington between astronomers Harlow Shapley and Heber Curtis. Shapley argued that the spiral nebulae were small structures within the Milky Way, which he believed was itself enormous, perhaps 300,000 light-years across. Curtis argued the opposite, that the spiral nebulae were independent galaxies, island universes comparable to the Milky Way in size, located at distances far beyond its boundaries. Both men made valid points. Both made errors. The debate ended without resolution. The answer came 3 years later from a young astronomer working at the Mount Wilson Observatory in California named Edwin Hubble. Hubble was methodical, precise, and extraordinarily patient. In 1923 and 1924, he used the 100-inch Hooker telescope, then the most powerful in the world, to photograph the Andromeda Nebula in unprecedented detail. Within those photographs, he identified a particular type of variable star, a Cepheid, whose brightness fluctuates in a regular cycle. Cepheid variable stars had been recognized a decade earlier by astronomer Henrietta Swan Leavitt as a remarkably useful cosmic ruler. Leavitt, working at the Harvard College Observatory, had discovered that the period of a Cepheid's brightness cycle is directly related to its intrinsic luminosity. A Cepheid that pulses slowly is intrinsically more luminous than one that pulses quickly. By measuring how long a Cepheid takes to complete one cycle, you can calculate how bright it actually is. Compare that intrinsic brightness to how bright it appears in your telescope, and simple geometry tells you exactly how far away it is. When Hubble applied Leavitt's period-luminosity relationship to the Cepheid he found in Andromeda, the answer came back unambiguous. The Andromeda Nebula was approximately 900,000 light-years away, far beyond the boundary of the Milky Way. The exact figure was later revised upward as calibration of the Cepheid scale improved, eventually settling at the current value of approximately 2.5 million light-years. But even Hubble's original measurement was enough to demolish the previous picture of the cosmos entirely. The Milky Way was not the universe. It was one galaxy among an uncountable number of others. The universe was not a dome of fixed stars. It was an unimaginably vast structure, populated by billions of island universes, each comparable to our own home, all of them separated by distances that made the previously known scale of the solar system look like a rounding error. The implications took years to absorb. Hubble continued mapping the redshifts of these external galaxies and in 1929 published the relationship that now bears his name. The galaxies were not merely distant. They were receding, and their recession velocity was proportional to their distance. The farther a galaxy, the faster it moved away. The universe was not static. It was expanding. Working backward from this expansion, physicists and mathematicians recognized that if space was growing now, it must have been smaller in the past. Smaller and denser and hotter. The mathematics pointed to a beginning, a moment when all the matter and energy in the observable universe was compressed into an unimaginably small and hot state from which it subsequently expanded. That beginning, now called the Big Bang, occurred approximately 13.8 billion years ago, according to the most precise current measurements. Within a single generation of scientific work, humanity went from believing the universe was a shell of stars surrounding the solar system to understanding that it began from a singularity 13.8 billion years ago and has been expanding ever since, currently containing approximately 2 trillion galaxies scattered across a volume 93 billion light-years in diameter. That shift in understanding represents perhaps the largest single expansion of the known world in the history of human thought, and it was made possible entirely by the patient measurement of variable stars in a fuzzy patch of light that astronomers had noticed in the sky for centuries without knowing what it was. The story of how we learned to measure cosmic distances did not stop with Cepheids. As astronomers probed deeper into the universe, Cepheid variable stars became too faint to resolve individually in distant galaxies, so they developed a hierarchy of measurement techniques, each one calibrated against the one before it, and extending the reach of measurement farther into the cosmos. This hierarchy is called the cosmic distance ladder, and each rung of the ladder builds on the rungs below it. Parallax measurements, the slight apparent shift in a nearby star's position as the Earth moves around the Sun, provide the most direct and geometrically unambiguous distance measurements, but work only for stars within a few thousand light years. Cepheid variable stars extend the reach to tens of millions of light years. Beyond that, astronomers use other standard candles, objects whose intrinsic brightness is known and can therefore be used as rulers. The most powerful of these is the Type Ia supernova. A Type Ia supernova occurs when a white dwarf star in a binary system accumulates enough mass from its companion to trigger a runaway thermonuclear explosion. Because the explosion always occurs at approximately the same critical mass, Type Ia supernovae produce approximately the same peak brightness every time they ignite, regardless of where in the universe they occur. They are, in effect, standard candles of known wattage scattered through the cosmos. By comparing how bright they appear in the telescope to how bright they are known to be, astronomers can calculate distances out to billions of light years with impressive precision. It was precisely through observations of Type Ia supernovae in distant galaxies in 1998 that 2 independent research teams, one led by Saul Perlmutter and one by Brian Schmidt and Adam Rees, made the discovery that earned them the Nobel Prize in Physics in 2011. The expansion of the universe is not slowing down under the influence of gravity as expected. It is accelerating. Something is pushing space apart at an increasing rate. That something was named dark energy. The discovery of cosmic acceleration changed everything about our understanding of the universe's long-term future. Before that discovery, cosmologists entertained serious debate about whether the universe would expand forever or eventually slow, halt, and collapse back on itself under gravity. After 1998, the answer became clear. The universe will expand forever. not just at a constant rate, but at an accelerating one. Dark energy, whatever it ultimately turns out to be, is growing in influence relative to matter as the universe expands. The galaxies beyond the local group are not merely moving away, they are moving away faster every year. The isolation between galactic islands is not merely permanent, it is worsening on a schedule that the laws of physics appear to make irreversible. What dark energy actually is remains the deepest unanswered question in modern physics. The most mathematically natural explanation is that it represents the energy density of empty space itself, a concept Albert Einstein introduced into his equations of general relativity in 1917 under the name the cosmological constant, and then famously retracted when Hubble's discovery showed the universe was expanding. In its modern form, the cosmological constant is not a mistake, but a genuine physical quantity. The energy that empty space possesses, even in the complete absence of matter and radiation. Quantum field theory, the framework that describes all known elementary particles and forces, predicts that empty space should indeed have a non-zero energy density due to quantum fluctuations. The problem is that the quantum field theory prediction is off from the measured value by somewhere between 50 and 120 orders of magnitude, depending on how the calculation is done. This is often called the worst prediction in physics. The observed value of dark energy is almost unimaginably smaller than theory naively suggests it should be, and no one yet understands why. Alternative explanations include the possibility that dark energy is not a constant, but a dynamical field, one whose strength changes with time and whose value today is simply where that field happens to be in its evolution. This class of models goes by the name quintessence. If dark energy is quintessence rather than a cosmological constant, its strength might eventually change, potentially altering the fate of the universe. Some models predict that a dynamical dark energy could strengthen over time, eventually becoming powerful enough to tear apart not just the cosmic web, but galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms, in a scenario called the Big Rip. Other models suggest it could weaken and allow gravity to eventually halt the expansion. The current observational data cannot yet distinguish between these scenarios with certainty, though ongoing surveys like those being conducted by the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are narrowing the constraints with each passing year. What we do know is this: whatever dark energy is, it constitutes approximately 68% of the total energy content of the observable universe. Dark matter makes up approximately 27%. All the ordinary matter, every atom of every planet, star, gas cloud, and living thing in the cosmos amounts to approximately 5%. The universe is, by energy content, 95% things we do not yet understand. We have named them. We have measured their effects with extraordinary precision. We have mapped the structures they create and the isolation they enforce. But we do not know what they are. The darkness between galaxies is not just a spatial emptiness. It is an epistemic one. The universe is mostly made of things that remain, for now, beyond our complete understanding, dark matter, despite being invisible to every electromagnetic instrument ever built, is in many ways better understood than dark energy, at least in terms of its gravitational effects. We know dark matter exists because the universe cannot be explained without it. Galaxies rotate too fast for the visible matter they contain to hold them together. The stars in the outer regions of spiral galaxies move at speeds that should fling them into the intergalactic void if only the luminous matter were present. Something else, something massive and distributed in a roughly spherical halo around every galaxy, provides the additional gravitational pull that keeps the stars in place. That something is dark matter. In clusters of galaxies, the amount of mass required to explain the observed gravitational lensing of background objects is far greater than the mass visible in stars and gas. The difference is dark matter. The cosmic microwave background, the afterglow of the Big Bang, carries encoded within its temperature fluctuations, a precise record of how matter was distributed in the early universe. And those fluctuations are consistent only with a universe in which dark matter is roughly 5 times more abundant than ordinary matter. Dark matter does not just hold galaxies together, it built the cosmic web. In the early universe, dark matter's gravitational influence amplified the tiny quantum fluctuations that seeded the large-scale structure of the cosmos. Because dark matter does not interact with light, it began clumping under gravity while the ordinary matter was still being pushed around by radiation pressure. The dark matter formed the scaffolding first, and the ordinary matter fell into it later, like sand settling into a preformed mold. The filaments and nodes and walls of the cosmic web trace the distribution of dark matter. The galaxies formed inside the dark matter halos. The voids exist where dark matter density is low. The entire architecture of the universe, including the isolation between its galaxies, reflects the gravitational signature of a substance that emits no light and has never been directly detected. Despite decades of searching, no dark matter particle has ever been observed in a laboratory. The most theoretically appealing candidates, weakly interacting massive particles called WIMPs, have been hunted in underground detectors shielded from cosmic rays and in collisions at particle accelerators, including the Large Hadron Collider at CERN. They have not been found. This null result has progressively excluded the simplest WIMP models and pushed the search toward either heavier or lighter candidates, or toward entirely different dark matter candidates such as axions, sterile neutrinos, or primordial black holes formed in the early universe. The search continues, but the theoretical landscape has grown considerably more complex since the original WIMP hypothesis seemed almost certain to succeed. What is not in doubt is that dark matter is there. Its gravitational effects are measured with precision from galactic to cosmological scales. The cosmic web could not have formed without it. The large-scale structure of the universe, the filaments and voids and clusters that determine the spacing and isolation of galaxies, was sculpted primarily by a substance that remains invisible and unidentified. The darkness between galaxies is, in a very literal sense, shaped by darkness. The relationship between dark matter, dark energy, ordinary matter, and the voids they collectively create is perhaps most vividly illustrated by the history of the Coma supercluster and the Great Wall. In 1989, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics was added through redshift measurements. In front of and behind this sheet of galaxies lay enormous voids, regions of near-total emptiness hundreds of millions of light-years across. The discovery shattered the assumption, still common among cosmologists at the time, that the universe's matter was distributed in a roughly homogeneous way on large scales. Instead, the cosmos had a pronounced architecture, a foam-like structure of thin walls and filaments surrounding enormous empty bubbles, exactly as the cold dark matter model of the universe had predicted, but which had not yet been confirmed observationally at this scale. The Great Wall and the voids surrounding it demonstrated that the isolation between galaxies was not a local peculiarity of our neighborhood. It was a universal feature of the cosmos, repeated at every scale the surveys reached. Subsequent surveys pushed the boundaries of this mapping exercise further and further. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and the Baryon Oscillation Spectroscopic Survey collectively mapped the positions of millions of galaxies across billions of light-years, assembling the most detailed 3-dimensional map of the large-scale structure ever constructed. Each new survey revealed more of the cosmic web in finer detail and confirmed the same fundamental result. The universe is organized into a foam of empty voids bounded by thin sheets and filaments of galaxies, and the voids account for the overwhelming majority of the total volume. The Sloan Great Wall, discovered in 2003, is even larger than Geller and Huchra's original discovery, stretching approximately 1.4 billion light-years in length. It represents one of the largest known structures in the observable universe, and it is separated from neighboring structures by voids of comparable scale. These surveys also revealed something subtle but important about the voids themselves. They are not all the same. Voids vary considerably in their depth, their size, and their evolutionary state. Some are relatively shallow underdensities where the density is perhaps 30 or 40% below the cosmic average. Others are much more extreme, with densities dropping to a few percent of the cosmic average in their deepest interiors. The deepest voids evolve differently from shallower ones. In the deepest voids, gravity is so weak relative to dark energy that the interior matter does not even attempt to collapse into structure. It simply continues to disperse, becoming progressively emptier as the void expands, and the few remaining particles are pushed outward toward the bounding walls. The galaxies that do manage to form inside deep voids tend to be distinctive objects. Void galaxies, as they are called, are systematically different from galaxies in denser environments. They tend to be bluer, indicating more recent star formation, possibly because they have not been affected by the gravitational interactions and ram pressure stripping that tend to shut down star formation in cluster galaxies. They tend to be less massive, having grown without the mergers and accretions that build larger galaxies in dense environments. They rotate in more orderly ways because they have not been disturbed by close encounters. They are, in a sense, galaxies in their purest form, evolving in isolation from the messy gravitational dynamics that characterize denser cosmic neighborhoods. Studying void galaxies offers a kind of controlled experiment in galaxy evolution, revealing what galaxies look like when the environment is stripped away. But void galaxies are also the loneliest objects in the known universe. A galaxy sitting at the center of a deep supervoid faces emptiness in every direction for hundreds of millions of light years. Its nearest neighbor galaxy may be separated from it by a distance that would take light tens of millions of years to cross. Its view of the cosmos, while unobstructed by dust or the light of neighboring galaxies, reveals almost nothing. The surrounding void stretches to the horizon and beyond, interrupted only by the faint glow of the galaxy itself, reflected back from dust and gas in the outlying regions. If such a galaxy hosts a civilization capable of building telescopes, that civilization faces an observational desert. The cosmic web beyond the void's walls is detectable, but faint, distant, and difficult to map in detail. The evidence for cosmic expansion is present but sparse. The picture of the universe such a civilization would construct, from its vantage point in the void's interior, would be subtly but systematically different from the picture constructed by an observer in a denser environment. This thought, that the physical location of an observer within the cosmic web influences what cosmological conclusions they can draw, is a genuinely unsettling one for the practice of science. Science depends on the assumption that the laws of physics are the same everywhere, that an experiment conducted here produces the same result as the same experiment conducted a billion light years away. That assumption is almost certainly correct, but the data available to confirm it, the observations that allow an observer to test their cosmological models against reality, are profoundly shaped by where the observer sits in the cosmic web. We happen to sit in a slightly underdense region, the KBC void, which some researchers argue may introduce a systematic bias into local measurements of the Hubble constant, potentially contributing to the Hubble tension. The universe does not present itself identically to all observers. The cosmic web ensures that different observers, depending on their location within filaments, walls, clusters, or voids, see different slices of the cosmos with different degrees of completeness. The Hubble tension itself deserves a careful examination because it sits at the intersection of cosmic distance measurement and our deepest uncertainty about the universe's expansion. The Hubble constant is the number that describes how fast the universe is expanding, expressed as a velocity per unit distance. Measuring it sounds straightforward, but has proven to be one of the most contentious problems in modern cosmology. Measurements, using the cosmic microwave background and the physics of the early universe, consistently yield a value of approximately 67 kilometers per second per megaparsec. Measurements using the cosmic distance ladder, calibrated with Cepheid variable stars and Type Ia supernovae in the local universe, consistently yield a value of approximately 73 kilometers per second per megaparsec. The discrepancy is small in absolute terms, but large in statistical significance, and it has stubbornly refused to go away as measurement precision has improved. If both sets of measurements are correct, and the discrepancy is not due to systematic measurement errors, then something is wrong with our standard model of cosmology. The universe may have expanded at a different rate at different epochs than the standard model predicts. There may be new physics, perhaps involving dark energy, dark matter, or unknown particles, that alters the expansion history in ways not captured by current models. The resolution of the Hubble tension is one of the most actively pursued problems in observational cosmology, and it matters directly for our understanding of intergalactic distances, because the Hubble constant is the primary tool used to convert galactic redshifts into distance measurements. If the constant has a different value than currently accepted, the scale of the entire observable universe and the distances between its galaxies would need to be revised accordingly. The measurement of cosmic distances continues to improve with every new instrument and every new technique. The James Webb Space Telescope, launched in December of 2021 and achieving full science operations in 2022, has transformed our ability to observe galaxies at extreme distances. Webb can detect galaxies that formed when the universe was less than 300 million years old, a mere 2% of its current age. These objects are so distant that their light has been traveling for more than 13.5 billion years before reaching Webb's mirrors. They represent the first generation of galaxies to form after the Big Bang, the earliest islands of stars to condense from the primordial hydrogen and helium that flooded the young cosmos. What Webb has found in these early galaxies has surprised the astronomical community. Several galaxies detected in Webb's deep field images appear to be larger and more massive than standard models predicted for such an early epoch. Galaxies that should have been small and irregular, still in the early stages of assembling their stellar populations, instead appear to contain hundreds of billions of stars already formed within the universe's first few 100 million years. This suggests that galaxy formation may have proceeded faster in the early universe than current models capture, a finding that is driving active revision of the theoretical frameworks used to describe how the cosmic web assembled itself in the aftermath of the Big Bang. The discovery has practical implications for our understanding of the voids as well. If galaxies formed earlier and more rapidly than expected, the process of evacuating matter from the regions that became voids may also have proceeded differently than modeled. The relationship between early galaxy formation and the development of the large-scale structure, including the depth and distribution of voids, is an area of active research that Webb's observations are reshaping in real time. The early universe, it turns out, was a more dynamic and rapidly evolving place than the standard models suggested, and understanding precisely how it evolved will refine our picture of why the voids are where they are and how deep they became. Webb is also providing new data on galaxies at intermediate distances, galaxies formed a few billion years after the Big Bang, when the cosmic web was already partially assembled, but still quite different from what it is today. These observations allow astronomers to trace the evolution of the void filament architecture over cosmic time, watching in statistical detail as the voids have grown and the filaments have thinned. The data confirms the broad picture. The voids have been growing for most of cosmic history, the filaments have been thinning, and the isolation between galaxies has been deepening on the schedule that dark energy's dominance would predict. The universe we observe today is more isolated than the universe of 5 billion years ago, which was more isolated than the universe of 10 billion years ago. There is one more dimension of intergalactic isolation that rarely receives the attention it deserves, and it involves not light or matter but gravity waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves, ripples in the fabric of space-time produced by the collision of two black holes approximately 1.3 billion light-years away. This discovery opened an entirely new window on the universe, one that operates independently of light and electromagnetic radiation. Gravitational waves travel at the speed of light, but are produced by some of the most violent events in the cosmos: black hole mergers, neutron star collisions, and potentially processes in the very early universe. They pass through matter without being absorbed or scattered, making them in principle detectable from anywhere in the universe, regardless of what lies between the source and the observer. In the years since the first detection, LIGO and its partner observatories Virgo and Cagra have detected dozens of gravitational wave events, mostly black hole mergers. In 2017, the detection of gravitational waves from a neutron star merger was accompanied by a burst of electromagnetic radiation observed across multiple wavelengths, inaugurating the era of multi-messenger astronomy, the ability to study cosmic events through more than one type of signal simultaneously. This capability is scientifically transformative for events within a certain range. But gravitational waves, like light, face the fundamental constraint of the expansion of space. The gravitational wave signal stretches as it crosses an expanding universe, losing energy to the Hubble flow just as photons redshift. For sources at distances comparable to the visible universe, the signal arrives faint and stretched. For sources beyond the cosmic event horizon, no gravitational wave signal, no matter how powerful its origin, will ever reach us. Future gravitational wave observatories, including the proposed space-based Laser Interferometer Space Antenna, known as LISA, planned for launch in the mid-2030s, will dramatically extend the range of gravitational wave detection, potentially reaching back to events in the very early universe and detecting the signals from massive black hole mergers in galaxies billions of light-years away. But even this extraordinary new sense will not reach across the distances that separate us from the 94% of galaxies already beyond our physical reach. The universe has compartmentalized itself not just against physical travel and electromagnetic communication, but against every known form of information transfer. The laws of physics do not appear to offer a loophole. The most haunting implication of all of this is the one that takes the longest to fully arrive. We live on a planet orbiting a star in a galaxy that contains 400 billion other stars. Our galaxy belongs to a local group of over 140 galaxies. Our local group sits within the Laniakea supercluster, a vast gravitational flow pattern encompassing over 100,000 galaxies spread across 500 million light-years. Our supercluster is one node in a cosmic web containing an estimated 2 trillion galaxies spread across 93 billion light-years of observable space. By any reasonable measure, the universe is teeming with structure, with complexity, with the raw material from which worlds and suns and possibly life can emerge. And yet every single one of those 2 trillion galaxies is, for all practical physical purposes, an island, isolated from every other island by distances that grow larger every second, separated by voids so empty that the concept of a medium connecting them is almost meaningless, unreachable by any known physics within any time frame that matters to any civilization that might inhabit them. The abundance of galaxies does not make the universe less lonely. It makes the loneliness more profound because the companions exist but cannot be reached. The neighbors are there but cannot be visited. The signals are sent but cannot arrive within any meaningful span of time. 2 trillion campfires burning in the dark, each one warming its own small circle. Each one surrounded by a void that stretches without limit in every direction. Each one the only light its inhabitants will ever truly know. The universe did not have to be this way. In a cosmos with different physical constants, with a weaker dark energy, with a slower expansion rate, the islands might be close enough to see one another clearly, to communicate, to eventually reach across the gaps. We live in the particular cosmos that exists, the one where the constants have the values they have, and the expansion proceeds at the rate it proceeds. That cosmos is this one. Vast, beautiful, populated with structures of staggering complexity, and organized at its deepest level around a principle of isolation so thorough that it defines the experience of every observer within it. Scientists will continue to map the voids and measure the filaments. They will refine the value of the Hubble constant. They will probe the nature of dark energy with instruments of increasing precision. They will study void galaxies and early galaxies and the gravitational wave signals of merging black holes billions of light years away. Each of these efforts will deepen our understanding of why the universe is arranged the way it is, and how the isolation between its parts came to be. None of them will change the fundamental architecture. The voids will continue to grow. The reachable universe will continue to shrink. The cosmic event horizon will continue its slow advance, swallowing one galaxy after another into the permanent silence beyond. The fire burns, the darkness remains, and the distance between galaxies is not just worse than you think. It is worse than it is possible, in any intuitive human sense, to truly think. There is a particular moment in the history of observational astronomy that deserves more attention than it typically receives, because it perfectly illustrates the disconnect between what the universe looks like and what it actually is. In October of 1995, Robert Williams, the director of the Space Telescope Science Institute, made an unusual decision. He allocated 100 hours of time on the Hubble Space Telescope, roughly 10% of the telescope's annual discretionary budget, to stare at a single blank patch of sky in the constellation Ursa Major. His colleagues thought he was wasting a precious resource. The patch was carefully chosen to be as empty as possible, free from bright stars and known galaxies, a region of sky that appeared to contain nothing worth looking at. Williams pointed the telescope and opened the shutter for a total exposure spanning 10 days. The resulting image was the Hubble Deep Field. It showed approximately 3,000 galaxies in a patch of sky so small you could cover it with a grain of sand held at arm's length. 3,000 galaxies in a region that appeared completely empty to any telescope previously built. The image immediately transformed cosmology's understanding of galaxy counts. If that tiny patch was representative of the whole sky and subsequent surveys confirmed it was, then the total number of galaxies in the observable universe was not the few billion previously estimated. It was in the hundreds of billions. Later, more refined analyses using Webb's data pushed that estimate to approximately 2 trillion. The Hubble Deep Field is now one of the most reproduced scientific images in history. It appears in textbooks and documentaries and museum exhibits around the world. It is universally described as a testament to the richness of the cosmos. And it is. But it is also a perfect demonstration of the illusion that photographs create. Every galaxy in that image appears close to every other galaxy in the frame. Your eye automatically groups them, notices patterns, imagines relationships. The brain performs its ancient pattern recognition function and concludes that those objects are near one another. They are not. The galaxies in the Hubble Deep Field are spread across billions of light-years of depth. Some of them formed when the universe was less than 1 billion years old. Others are relative neighbors, a few 100 million light-years distant. Between any two galaxies in that frame that appear side by side, the actual three-dimensional separation might be hundreds of millions or even billions of light-years of expanding void. The image is beautiful. The image lies. And the lie is not a failure of the image, it is a failure of human perception when applied to cosmic scales. We evolved to perceive a world where the distances we could see were also the distances that mattered. The predator that appeared nearby was nearby. The fruit that looked close was close. Nothing in 4 billion years of evolution on the surface of a small rocky planet prepared our visual systems to correctly interpret the depth cues hidden in an image that spans billions of light years of cosmic history. The depth is invisible. The isolation is invisible. The overwhelming emptiness that defines the universe is, by its very nature, invisible. You cannot photograph a void. You can only photograph the rare bright exceptions at its edges. This invisibility of the void has a peculiar effect on the psychology of anyone who spends time thinking seriously about cosmology. The first encounter with the true scale of intergalactic distance tends to produce a kind of cognitive vertigo, a sense that the familiar universe of photographs and documentaries and telescope images has been revealed as a pleasant fiction. The second encounter, after the initial shock has settled, tends to produce something more nuanced. Not despair exactly, but a recalibration, a quiet adjustment of expectations about what the universe owes to its inhabitants. The universe does not owe us proximity. It does not owe us reachable neighbors. It does not owe us a cosmos organized for the convenience of the creatures that evolved to wonder about it. What it has given us, instead, is the capacity to measure the distances we cannot cross, to map the voids we cannot enter, to name the galaxies we cannot visit, and to understand in mathematical detail precisely why we cannot reach them. That capacity, the ability to comprehend the full scope of our own isolation, is itself one of the most extraordinary things in the known cosmos. No other phenomenon we have discovered is capable of knowing it is isolated. No star, no black hole, no supercluster possesses the ability to recognize its own place in the cosmic web, to measure the distances to its neighbors, to understand the physics of why those distances are growing. Only life, and specifically intelligent life, accomplishes this. Only minds that evolve from chemistry that condense from dust, scattered by long-dead stars inside a galaxy, that form from quantum fluctuations in the infant universe. Only those minds can look outward and understand what they are looking at. That understanding does not shorten the distances. It does not slow the expansion. It does not build a bridge across the void. But it does something that nothing else in the universe can do. It bears witness. It registers the reality of 2 trillion isolated campfires burning in the dark and acknowledges that this is how the cosmos is built, not as a deficiency, but as a fact. Not as a tragedy, but as a description. The darkness between the galaxies is real. The isolation is real. The distances are growing, and we are here, briefly, with instruments precise enough to measure them and minds capable enough to understand what the measurements mean. That may be enough. It may in fact be everything. If the ideas in this exploration stayed with you, the most useful thing you can do is pass it on to someone else who would find it equally striking. The questions raised here are ones that physics is still working to answer, and every person who asks them seriously adds something to the conversation that matters. There is one final perspective that ties all of this together in a way that does not get discussed often enough in popular science. It concerns the relationship between cosmic time and cosmic isolation, and it reveals that the universe we inhabit today is, by the standards of what has existed before and what will exist in the future, an unusually information-rich moment. The universe is 13.8 billion years old. That sounds ancient. By human standards, it is incomprehensibly old. But by the standards of stellar physics, it is middle-aged at most. The longest-lived stars, the small dim red dwarfs that burn their hydrogen so slowly and so efficiently that they can sustain fusion for trillions of years, have barely begun their lives. Some of them will still be burning hydrogen 100 trillion years from now, long after every star like our Sun has exhausted its fuel and collapsed into a cold, dark remnant. On this extended timeline, the current era of the universe is extraordinary for one reason above all others. Right now, the universe is still young enough that the evidence of its origins is fully accessible. The cosmic microwave background, the afterglow of the Big Bang, still permeates all of space. The large-scale structure of the cosmic web, the filaments and voids assembled over the first several billion years of cosmic time, is still intact and mappable. Galaxies at distances of billions of light years are still visible to our telescopes, their ancient light still arriving after journeys of up to 13.5 billion years. The universe's own history is written in the sky, accessible to any observer with sufficiently sensitive instruments. This will not last. The cosmic microwave background is already redshifting. Its photons, which were in the microwave region of the spectrum 13.8 billion years ago when they were emitted, are gradually shifting to longer and longer wavelengths as the universe expands. In 1 trillion years, they will have redshifted far into the radio spectrum, beyond the detection capability of any plausible instrument. In tens of trillions of years, they will be gone entirely, stretched to wavelengths so long that even the concept of detecting them becomes meaningless. The sky that any observer in the far future universe looks at will not contain this faint but information-rich fossil of cosmic origins. It will simply be dark, populated only by whatever stars happen to exist in whatever galaxy that observer inhabits. Similarly, the cosmic web that currently allows astronomers to trace the structure of the universe on its largest scales will not persist indefinitely. Dark energy is already thinning the filaments and growing the voids. Over hundreds of billions of years, the connections between galaxy clusters will dissolve. The walls and sheets of galaxies that surveys like the Sloan Digital Sky Survey have mapped in such detail will disperse. The large-scale structure will cease to be a useful cosmological observable. Future observers in the merged Milky Galaxy, looking out after the cosmic web has dissolved and the cosmic event horizon has swallowed every external galaxy, will inhabit a universe that looks nothing like the one we currently observe. Their sky will be full of stars, but it will be free of the cosmic context that gives our cosmology its depth and its history. In this sense, every observation made today, every survey conducted by the Sloan Digital Sky Survey, and the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope and the James Webb Space Telescope, and every other instrument currently pointing at the deep sky, represents an act of cosmic archiving. We are recording the universe's structure while it is still there to be recorded. We are measuring distances and mapping voids and counting galaxies in a window of cosmic time that will not remain open. The light arriving from the most distant galaxies Webb can detect left those galaxies before the solar system existed. We are receiving mail from a universe that no longer looks the way it looked when the messages were sent. And we are doing so at the one moment in cosmic history when the postal service is still operational. The irony is beautiful and quietly devastating. We arrived just in time to see the full picture. We evolved on a planet around a star in a galaxy that formed at just the right epoch to allow the large-scale structure to still be observable, the cosmic microwave background still to be detectable, the neighboring galaxies still to be reachable in principle even if not in practice. A few trillion years earlier would have meant no stable stars, no chemistry, no planets, no life. A few trillion years later, and the universe would have become too isolated, too dark, too stripped of its observational breadcrumbs for any cosmology deeper than the single inhabited galaxy to be possible. We live in the brief middle period when the universe is still legible. That legibility is itself a kind of gift, or at least a remarkable coincidence, depending on your philosophical inclinations. The universe does not know we are here. It is not preserving its history for our benefit. The cosmic microwave background is not a message left for us to find. The large-scale structure is not a map drawn for our use. These things exist because of physics, not because of intention. But they exist right now, during the era when minds capable of reading them happen to have evolved. And that fact is worth sitting with. We happened to arrive when the library was still open. We happened to develop the instruments to read the books while they were still on the shelves. And the books tell a story of a universe that is mostly void, mostly dark, mostly unreachable, and entirely real. The distance between galaxies is not a problem awaiting a solution. It is not a challenge that a sufficiently advanced civilization will one day overcome. It is the universe's fundamental architecture, written into the laws of physics by the values of the constants, reinforced by dark energy's relentless expansion, deepened by the age of the cosmos, and permanent by any reasonable definition of the word. The void is the universe's default state. The galaxies are the exceptions. The light is temporary. The darkness endures. We are standing at one of the exceptions, looking out at the rest of them, measuring the distances that separate us, and understanding for the first time in cosmic history what those distances actually mean. That understanding is finite. It will not survive the cooling of the stars, or the silencing of the last pulsar, or the final fade-out of the cosmic background. But while it lasts, it is the most extraordinary thing the universe has managed to produce. A brief, bright concentration of complexity that knows what surrounds it, knows how alone it is, knows the physics of the void in detail, and finds the whole arrangement worth examining anyway. The galaxies are out there. The voids between them are growing. The isolation is permanent and deepening, and the fire for now still burns.